Okay, it's about that time. Whoa, that's nice. Welcome back, everybody. As promised, I will try to do a little recap, and then we're going to launch into a new topic today and start talking about Lyapunov functions. So that's our next, we're kind of moving past dynamic programming and thinking about the next topic. So let me just sort of recap the dynamic programming ideas, and I'll make connections into what we're doing today. Dynamic programming view of optimal control. We talked over the couple lectures about three settings, right? We talked about the tabular setting, where everything was on a graph, a discrete graph. Right? And we made it a connection to using that on a mesh over continuous state space. And that was a very powerful tool, is a very powerful tool that'll take arbitrary dynamics, arbitrary cost functions, and solve them, within some numerical accuracy. The only pitfall there is that there's a curse of dimensionality. In particular, as the number of state variables increases, the cost of covering that high-dimensional state space with a dense mesh becomes unwieldy. It grows exponentially. So these methods run out after a handful of dimensions. We use the same dynamic programming principles to talk about the linear quadratic regulator, and we will more generally think about linear optimal control as an important setting. And this was incredibly powerful up to high dimensions, but it's restricted to linearized dynamics. I tried to make the point that that's often very powerful. It captures the long-term dynamics of even complicated systems, but there are some things it just can't capture. And then the last lecture, we talked about function approximators more generally. With neural nets being the most common choice these days. Okay. And just to summarize a few of the key points from that, right? So in both of these settings, we were able to think about exact value iteration in the sense that we would expect to get exact convergence, where we would have the dynamic programming Bellman equation have zero error, right? We would find on the graph or in the linearized dynamics, we would exactly zero the equation. In the function approximator case, we had to give that up a little bit, and we were doing a least squares, a gradient descent version of least squares value iteration, where I wrote that as saying we're going to define a loss function now, which is the sum over a bunch of sample points of the j our estimated cost to go, estimated optimal cost to go from being in some sample xi, minus the desired one, where there was some subtlety in how we computed that, right? But this is roughly the Bellman equation. But the point is, we can no longer make the function equal the desired value at all the points. We somehow have to just minimize a least squares residual. And we did that via gradient descent. So we said if this is parameterized by some parameters alpha, then we said we're going to change alpha in the direction of the gradient, where this is some, I don't think I remember to say the word learning rate last time, but eta was a learning rate. Okay, so these are exact dynamic programming in some sense, and this becomes an approximate dynamic programming. There's a special case where the least squares value iteration has very strong results, which is the linear function approximators. Okay, and that's actually a pretty powerful class. Okay, but in the full neural network case, we don't have those guarantees. It works well in practice, right? Especially when you get all of the tricks right about random weight initialization in the correct way, using the right optimizer, all of the tricks that the machine learning community have come up with. So why would you choose this over, let's say, the tabular case? I still have to sample at some points, right? Maybe the number of samples that I would have to address could grow just as badly as the cursive dimensionality on the mesh. And actually, I think it does. Like so that's true. I think you would expect to see the number of samples also grow. This is a more flexible thing, right? The mesh representation, you have to be a little bit careful. Like the implementation I gave you, for instance, you have to have like rectangular grid meshes. Okay, so it's like having sample points at very regular intervals over the entire state space, and that's a pretty significant constraint. This relaxes it. You can pick samples however you want over the state space, but if you want to cover the entire state space densely in high dimensions, that sampling requirement is going to still become painful. You can hope that with less samples, the magic of neural networks would find good functions, but I don't have a theorem for that. People have belief in that. I have a little bit of belief in that. Some people have a lot of belief in that. But I do think that this will still become painful at some point if you don't choose. You have to think about more carefully about how to choose xi. Yes?
In some sense, if you got, I don't know, really lucky with a small number of samples that you picked, the neural network approach could approximate the true function perfectly. But so in some sense, the tabular is limited not just by like the resolution, not just by the samples, but also it's directly tied to the resolution, right?
Okay, so that's a good question. So let's say I was looking over the class of polynomial cost-to-go functions. It might be that there's an incredibly clever set of samples. There are well-known clever sampling techniques that would give you an optimal number of samples to perfectly fit functions, right? And we don't have that in the tabular setting. Maybe we could have that here. But there's still a gap in what you say about, because it's hard to know that the true cost-to-go function lives in the class of functions that are from the polynomials or from the neural network or whatever. So I suspect, especially if we're fitting discontinuous cost-to-go functions and things like this, I suspect these are still going to be approximate. And so I think you could get less samples could do well, for sure, but I don't know if you'll have the strict guarantee. Okay. This also gives you a more compact representation. I mean, some neural networks are massive, but actually, compared to storing an entire mesh, I could just have a 16 by 16 by 2 kind of network or something could be a compressed representation of a high dimensional function. So there's many reasons to like this, and I'll try to give you the best implementation I can of that, so you can, if you want to play with that on your projects or anything like that. But there's still more work to do, and the problems are still hard. Okay. So today we're going to take the next step. We're going to talk about Lyapunov functions, Lyapunov analysis. And given that backdrop, we're going to talk through some of the mechanics of Lyapunov analysis, but I'll say it now, and I'll remind you at the end why it follows naturally from this. Okay. one of the things that is hard about solving optimal control problems is that you're trying to solve this partial differential equation. You're trying to be optimal, okay? The tools we'll talk about today are asking, maybe that's more than you really need. If you just wanted to relax the question and said, am I good enough to accomplish the task? Am I going to get to the goal eventually, right? And you didn't care about being optimal on your path to the goal, then you can make the problem easier. You can relax the requirement that you find a truly optimal solution and instead ask for, am I just good enough solutions, okay? That's one motivation. A second motivation would be, even if I want to be optimal, okay, and I've applied, let's say, my least squares value iteration, and I have something that I know is only approximately optimal, you could still ask the question, is my approximation good enough? Am I still, it's going to be close to optimal, but is it also going to accomplish the task? Can I certify that this controller is going to be successful? So you could even use these tools to certify approximate optimal controllers. Okay, so we're going to try to get bigger in the systems we can handle by giving up something a little bit, saying we're not going to ask for strict optimality, we're going to ask for a little less. I just want to say it's good enough. And you might be surprised, but questions about, is it good enough? Is my controller good enough to accomplish a task? Is my autonomous car going to hit a car, hit another car, or something like this? These are all closely, even though that sounds very different, these are closely related to the analysis of the stability of a dynamical system. Okay, so you might be surprised, but we're going to start this whole conversation. I mean, if you know Lyapunov, you won't be surprised, but these general questions of, are my controllers good enough, can often be framed in the language of stability analysis and the generalizations of that follow. So remember when we talked about fixed points, different types of stability of fixed points, regions of attraction. It turns out that's the language you want for asking, are my controllers good enough to accomplish a task? So let's start with my favorite examples, and just think about a little bit more about how do we make stability arguments for some of the nonlinear systems we've already looked at. Okay, so let's just think about stability analysis of the pendulum. Nonlinear stability analysis now. Okay, so if I think the damped pendulum here, my equations of motion, I'm going to write them slightly differently today. The friction term, the damping term, I'm going to go ahead and write over on the right-hand side as if it's a force coming in. I want my damping to be positive if I'm going to expect this thing to be stable. So think of this as joint friction, right? Now, I said from the very beginning, the first lecture, that integrating this ODE is not something I can do in closed form. I can't tell you what theta is as a function of time, but I can still answer the long-term questions. And today, I want to give you the mechanics of answering those long-term questions, right? So, we know with high confidence that it's going to end up at the bottom if it has friction, but how do you prove that? If you didn't have that mechanical insight, how would you prove that? And with the pendulum, it's very natural to just think about mechanical energy, okay? So let's think about the mechanical energy of this system. So I'm going to have 1/2 ml squared theta dot squared. This is the kinetic energy. That's just 1/2 mv squared, but when you're a rotary joint, you get L squared theta dot squared, okay? And then I'll actually write it to make that match. I get the potential energy looks like mgl cos theta. Okay, so this is a function that we can reason about. It's a scalar function, right? It depends on theta and theta dot. But I can just, by quick inspection of the algebra and understanding of the physics, I can look immediately and say that this thing is always going to be greater than negative mgl. That's the configuration when I'm at the bottom here, because that cosine is going to be between -1 and 1. So the worst it can do is make this thing negative mgl, right? And theta dot is, this thing is only positive, right? So the lowest that energy can ever be is negative mgl. It's a little weird that I have my coordinate system like that, but to make those match, I did it, okay? So this, importantly, the function is bounded below, okay? You can't have negative infinity energy. And then the interesting thing is, let's look at the rate of change of the energy, okay? So let's look at how the energy changes over time. Okay, so I can just take the derivatives of this. I get ml squared theta double dot times theta dot, okay, plus theta dot mgl sine theta. That's the time derivative. But it happens, and it's not an accident, this term here is also this term here. So if I want to substitute in the dynamics here, then I'll just write that whole thing. This thing has to equal negative b theta dot minus mgl sine theta. That's just substituting in the equations of motion. So that thing gets multiplied by the theta dot. And guess what? This term cancels this term. And the whole thing just comes out to be negative theta dot squared, b theta dot squared. Now, if you're mechanically inclined or know your mechanics, that's not surprising, right? So this is saying the rate of change of energy is b theta dot squared. Another way to think about this is torque times velocity. That's the rate of change of energy. That's what it should be, okay? Interestingly, this thing should always be less than or equal to 0. It's nice having these squared terms. They make the analysis very simple, okay? So that gives me a lot, right? So what are the implications of all that? Remember the phase portrait of the pendulum. Right? It has this going on. Okay, so let's use these facts to try to make some arguments, right? So first of all, what are these contours? Remember, these are the contours of constant energy. So this is actually E equals mgl. That one I can fill in. This might be E equals, I don't know, mgl over 2. And this is E equals 0.02 or something, I don't know. Right, these are contours of constant energy. And I know that, so think of this now as, we know that the energy is at its minimum here at the downward. And these are these are the contour lines, right? So this is like a bowl coming out here, right? Is that picture clear to people? Yeah? And those are the level sets of the bowl, those lines. Okay, so I know that energy dot is only going down. So if I start inside here, by just looking at the energy, I can guarantee that no trajectories are going to leave that set. Leaving that set out here would mean going up in energy. But we have a proof here that it's only going down. Okay? It obtains a minimum here, and it's going, well, let's see. If I could say that this was always negative, then that would be enough to say for sure that it gets to the bottom. It's a little subtle that this is less than or equal to 0, but you can still show that it will always get to the bottom. We know it should always get to the bottom. Okay? So let's think of the easy case first. Let's say that was strictly less than 0. Do you understand the argument that I'm in a bowl? That bowl is defined. I'm saying I'm always getting smaller in the bowl, except for when I get to the bottom, that would mean theta dot equals 0, and I'm at the bottom and I stop. Right, so I'm doing gradient descent on this bowl effectively, a form of gradient descent. At least I'm going downhill, and I'm going to get to the bottom. That's a way to certify the stability of this with equations that's going to scale. That idea is going to scale to much more complicated systems. Let's just think for a second. We're going to do it carefully at the end with the proper theorems, but let's just think for a second about the implications of this being less than or equal to 0. Okay, so this is strictly less than 0 when theta dot is non-zero, but it's equal to 0 when theta dot equals 0. So if I look along the line here, right, so theta dot equals 0 is this line here. Let's just draw it like this for a second here. Okay, so everywhere except for on that line, I know that I'm at least going a little bit down the bowl. When I'm on the line here, I'm actually not going, I'm just going potentially parallel to the bowl. I know I'm not going up, but E dot is just 0 when theta dot is 0. So what I'm expecting is orbits that go like this and go in. It's true that when they cross this line, they're not actually actively going down. But the argument goes like this, and we're going to make it formal later, okay? The only place that I can, when I cross the line here, I instantaneously stop going downhill, but I also continue into a place where I am going downhill. Okay, so I can't stop here. That's not a fixed point. I can't stop there and stop going downhill forever. I'm going to transit through the place where I'm not going downhill and get back to a place where I'm going downhill. And as long as the total time that I'm in is in a time where I'm going downhill dominates, then I'll get to the bottom. Okay. I think that's very simple, but it's important to sort of understand because we're going to make that machinery work in a much more general form. And that's what Lyapunov analysis does. So we're going to generalize this energy argument with Lyapunov functions. Okay, so now arbitrary dynamical system. Say if I'm given x dot equals f of x, I'm not going to think about u right now. I'm going to think about closed loop systems. We'll add the u's back in later, okay? And I want to prove that, let's say, x star equals 0 is stable, a stable fixed point. I want to prove stability of the origin. Okay? It turns out if you can find an energy function, if you find B of some differentiable function, we'll call it V, such that v at the origin equals 0. And for all x that are not at the origin, the function is positive. So I want it to be a bowl going up. And more importantly, or also importantly, I'm going to say that the derivative at the origin is 0, the time derivative. This is dv dt, right? This is going to be true if it's a fixed point. And for all x not equal to 0, I can say it's going downhill. Then that turns out to be enough. That function gives me a certificate. Then x star is stable. Remember, there's a couple different ways we could talk about stability. We talked about stability, asymptotic stability, global, exponential stability, all these other things, right? But maybe you won't be surprised that a Lyapunov function immediately tells me that x star is stable in the sense of Lyapunov. Okay? In the sense of Lyapunov. Okay, so we're going to work with this and massage this and understand this in a few examples. But this notation is a little gross. I wanted to write it once, but in general, I'm going to use the same notation that we use for positive definite matrices for positive definite functions. So a function is a positive definite function is one that's 0 at 0, but for all other x's, it's positive. So I'll use my same kind of matrix notation to say this is a positive definite function. That's standard notation. I didn't just make that up. Okay? And so I could similarly write that v dot of x is less than or equal to 0. Okay, so why is that function, having that, the existence of that function enough to prove stability, or why is it related to stability in the sense of Lyapunov? Do you remember stability in the sense of Lyapunov? You remember the?
What's the relation between v and f?
V is independent of f in some sense, but in order for these conditions to hold, v dot dv dt, v doesn't depend directly on time. The only way that v goes downhill is you'll see that dv dt, we're about to do it in a second here, but let me just write it right now. This is partial v partial x, f of x. That's probably the one spot of the board that you can't possibly see from your angle, but I'll write it again in a minute. Okay, it only comes into the time derivative is the short answer. That's how it came in for the energy of the pendulum too. I wrote an energy function, and E dot, the rate it went downhill was because of the dynamics. Okay, so the stable in the sense of Lyapunov, remember the epsilon ball, delta ball, all that business, okay? So x star is stable ISL if for every epsilon small, there exists a delta, greater than 0, such that if the initial conditions are inside the delta ball, then for all t, it's in the epsilon ball. Okay, so let's connect that to this idea here. Why does the Lyapunov function imply stability in the sense of Lyapunov? Let me draw two states, x1 and x2, and I'll draw just two or a couple. Let's see, these are my Lyapunov functions. This could be v equals 1, v equals 2. Right, these are just level sets of the Lyapunov function. If I have this function, just like the energy function, if I know that v dot is always less than or equal to 0, then every level set of my Lyapunov function is an invariant set, okay? In particular, once I have that property, then for any x where that v of x is less than or equal to some rho is an invariant set. What do I mean by an invariant set? If you start inside that set, you will never leave that set. Okay? Trajectories that start inside this set will never leave because in order to leave, v would have to go up. And I know v dot is going down, or is less than or equal to 0. Okay, so in the language of these epsilon delta balls, the game becomes, so if you tell me an epsilon, I'll say epsilon's going to have to be a perfect circle. These are balls. Epsilon ball. Those are the points that are within distance, Euclidean distance, if you will, from the origin, less than epsilon. If I have a Lyapunov function, then what do I do, right? I can find any contour of my Lyapunov function that is strictly inside this, and I know for sure I won't leave it. Right? The fact that this is an invariant set gives me the ability to answer these kind of questions. But just to be extra careful, right? So in order to find a delta ball, I actually have to find a delta ball that's strictly inside my contour of my Lyapunov function, which is strictly inside the epsilon ball. That's good. Good stuff. You guys don't look like you're excited about that, but okay. Right. If I start inside here, I know I'm inside the one sublevel set. And so since I have a function that says I can't go outside, I can't go up, that means I'm going to be inside this, which means I'm going to be inside this. Okay? So if you were able to find that v, then you've certified that you're stable in the sense of Lyapunov. Yes?
So in some sense, Lyapunov stability depends on our choice of norm, right?
Whether you're Lyapunov stable or not should not depend on that. And that's actually the reason we're playing this game is because you can pick a norm here, and if the Lyapunov function exists, you could think of this as this game of inner and outer is just so that if you have circles in some norm, I can convert that into my Lyapunov coordinates and then back into your norm, right? So it's actually the two balls exist just to be robust to the norm, in a sense. Yes?
Yeah, I guess not sure if this question will make sense, but is there a reason that Lyapunov stability is defined in terms of like these delta versus epsilon balls instead of like the value of like your potential function or like your level sets?
Yep. So it's a good question. So the question is why do we define it in terms of these epsilon and delta balls? So I think in practice, you can, once you have the concept of Lyapunov flying around, you can just talk about sublevel sets. This is a general concept that must be true. It's like, okay, imagine you're Lyapunov, right? And you're like, I've realized there's this property that requires finding some function v. If I want to explain Lyapunov stability, but not even to tell people about Lyapunov functions, then this is an easy way to do it, okay? But so that's a general way to say it without having to invoke the power of Lyapunov. The Lyapunov function helps you prove it, but that statement can be analyzed independently. Okay, we also talked about local stability versus global stability, and even regions of attraction, right? So the condition of v dot, these conditions of v of x greater than 0, v dot of x less than or equal to 0, can hold for all x inside some domain D. And it might not be all states, Rn. So if I could prove to you that those conditions held just in some region, D, as long as it contains the origin and has finite volume, then I can say something about the local stability of that. Because epsilons and deltas are small. Right? So if I only certified the properties in a little region, I could still say that that fixed point is locally stable. As D grows to some finite large volume, I can say something else. I can say something about a regional property of the system. And if D is the entire space, then I can say something about global stability, potentially. Okay, so these conditions need not hold globally. I can say something about local stability without them holding globally. Okay. We know that the pendulum is not just stable in the sense of Lyapunov, it's actually stable asymptotically. And it would be kind of a bummer if all this Lyapunov stuff didn't help us also talk about those other types of stability. Turns out a very minor modification allows you to talk about asymptotic stability or exponential stability, right? So asymptotic stability says not only that I'm going to stay near the fixed point, but I'm actually going to get to the fixed point as time goes to infinity. Okay? So it turns out the conditions are almost the same. It's just that I'm going to go to v dot of x is strictly less than 0. Right? The conditions before for ISL were just that I had to be less than or equal to 0. But now I'm saying I actually have to be going downhill. There's something that you will see in papers that if this holds for all states in R, okay, if it's for all x, then you can be globally asymptotically stable. Which you'll often see written as gas. You see papers, with gas in the subject or in the abstract or anything like that. Yeah, globally asymptotically stable. So this happens if D is the entire space, if those conditions hold, this is for all x in some domain D. If D is everything, then you can and these conditions match, you can be globally asymptotically stable. There's one other condition. That I won't dwell on. But it turns out to rule out some quirky cases, you also have to have the property that your v goes to infinity as x goes to infinity. Otherwise, you can have things like where you very slowly go downhill while you're not going, it's mostly a technical condition. How would we do exponential stability? Yeah.
V dot, I guess less than negative delta of V.
Okay. So v dot is if v is greater than 0, and then v dot of x is less than negative, actually even less than or equal to negative v of x. Is another condition that can hold. Why is that enough to prove it? Okay. because that means that the value of v at time at xt is going to be less than or equal to the value at x0 times e to the negative alpha t. As long as this says my value function, or sorry, my Lyapunov function is going down at some rate, some linear rate, or it's bounded by some linear rate, that means that I'll get there with some rate. I'll converge on the origin at some rate. Okay, that's the rough mechanics, right? Just think about the energy function of the pendulum and realize that there's other systems that don't have a mechanical energy interpretation, but if you can find some function that's kind of energy-like, then you can talk about, I'm actually going to get to the fixed point. You can talk about getting there, or just in the sense of Lyapunov, you can get there asymptotically, you can even get there exponentially. All the things work. Instead of finding a cost of a go function, we're now in the search for Lyapunov functions. And what I want to convince you by the end is that that's easier, right? There are many Lyapunov functions that can certify a system, but there's only one optimal cost to go function up to the scaling. All right, let's just crank out a few examples just to make that less abstract, and so you can see, I'll do it here so you can see the partial v partial x, which I promised. All right, simplest example. Let's just say I have the trivial linear system. Okay, and just if I draw my flow on a line, this is a one-dimensional system, so I can draw my flow on a line that just looks like -1. It has a fixed point at the origin, and I know it's stable because of all that graphical analysis we did before. But the picture doesn't count. I need a proof that it's stable, and I even want to talk about its rate and things like that. How do we do it with Lyapunov functions? You remember the first thing I did with optimal cost to go is I pulled a couple functions out of a hat, and then I had to slowly convince you that they were okay. Yeah, I'm going to do that again. If you choose v of x to just be x squared, turns out linear systems always have quadratic Lyapunov functions, okay, if they're stable. And you can think of that as, if I were to draw v of x, right, this is just a quadratic bowl like this, and you could sort of think about, the energy here is going down. The dynamics of this are equivalent to going downhill on a quadratic potential. But let's just work the mechanics. So v dot of x, dv dt, v doesn't have an explicit dependence on time, but the full derivative is partial v partial x. X dot, x does have a dependence on time, and it comes from the dynamics. Okay. In this setting, it's very easy to work with. It's just 2x times my dynamics is negative x, right? Negative 2x squared, which is, in fact, I can even write using my positive definite function notation. This is a positive negative definite function. Sorry, yeah, a negative definite function. Okay. And in fact, if you want to show that it's exponentially stable, right, you could say that this is less than or equal to negative alpha times v of x, right? It's just where alpha is 2. So it's exponentially stable, and the rate is given by 2. Yeah? Is that landing? Okay. Slightly better, more interesting example. Let's do a nonlinear system. Let's do x dot equals negative x plus x cubed. If I draw this x versus x dot, think about what that function needs to look like. When you're near the origin, the linear term dominates. And when you're away from the origin, the quadratic, or the cubic term dominates. So it looks like a negative x near the origin, and it looks like x cubed away from the origin, and it looks like it goes like this. Okay, and these cross. It's 0 at 1 and negative 1, and at 0. Okay, so the flows go like that. So we're going to we see immediately that this is a stable fixed point. And moreover, that the region of attraction of that fixed point the ROA of that fixed point, region of attraction, is all x in negative 1 to 1. Every initial condition between, but not including negative 1 and 1, will get to that fixed point. Okay, we can prove that. Here it's obvious from graphical analysis, but in more complicated systems we can prove that using Lyapunov functions. And it turns out, if I just do b equals x squared again, I can actually get this completely. Okay, so then v dot of x is partial v partial x. So it's partial v partial x is 2x times negative x plus x cubed. This is just negative 2x squared plus 2x to the 4th. I could also write that as 2x squared minus 1. I think I got that right. It's a little bit of a funny function, but if I plot that function, this is v dot of x. Turns out it's 0 here. Let me do it in a different color. 0 here, and then it's 0 again at 1 and 1. It does this something like this. This is 1, negative 1. Okay, but it's easy to certify that when x squared is less than 1, this thing is negative. Okay, so now what we have is a Lyapunov function that holds over the domain D, which is in this domain is going to be not inclusive, negative 1 to 1. Okay, and that's going to, what I'm going to give you that formal statement, but that's going to say that that domain is inside the region of attraction of the system. Those conditions are sufficient for me to say that's inside the region of attraction. Since this is less than or equal to 0, it's even a negative definite function for all x in negative 1 to 1. That actually is a certificate that that this set for all x -1 to 1 is inside the region of attraction. Okay. If you want to prove that an autonomous car doesn't crash or your Atlas robot doesn't fall over, it's going to be the same mechanics, okay? We're going to try to find some region of attraction of reasonable behavior by finding Lyapunov functions in really big spaces, potentially, okay? But the mechanics are this. Yes?
How do you pick the events?
I pulled it out of a hat here. There are some standard choices. We'll develop tools to search over them, the same way we develop tools for finding cost-to-go functions. And you can try to use neural networks, for instance. So there are many choices there. But for today, for this example, it was magic. Okay, so to make that statement, I need one more version of the Lyapunov function, of the Lyapunov argument. If I want to prove region of attraction, I need my conditions to hold. I need v of x greater than 0, v dot of x less than or equal to 0. Let's even say strictly less than 0 for the simplest case, okay? For all x in D, but I need to have D be an invariant set. And I'll draw a picture to make that clear, okay? So if D is an invariant set, if trajectories that start inside D stay inside D for all time, and this condition holds inside that set, then I know that I'm going to get to the origin, okay, that that's inside the region of attraction. That's a surprising thing, actually. You should appreciate. There's a bunch of subtle, I mean, maybe your mind is coming up with some counterexamples. That'd be great. But first, the reason why that invariant set condition matters is kind of the same thing we drew before, but let's just make it explicit here, okay? So if I have some two-dimensional state space, let's say I've got some region here where I've certified over this region that v dot of x is less than or equal to 0. Okay? That is actually not quite enough to guarantee that I'll get to the origin. It could be that there are trajectories in here still that leave. Why is that? Okay. There's another set of things I could potentially know. If I have level sets of V, for instance, if this is a V of x equals C level set, this is an invariant set. Any sub-level set of my Lyapunov function is an invariant set. If I start outside the invariant set, there's no guarantee. Just because v dot is going downhill, it could leave the set potentially. Okay? You need both things to be true. You need to know that v dot is less than 0, and I'm already inside an invariant set. V dot less than 0 by itself is not enough because you could be going downhill in your Lyapunov function, but get to a state later where you're going uphill. Right? Unless you can guarantee that you're not going to, in a future state, go into the uphill case, then you don't have a certificate. So those two things combined work. And the standard way that we work with these invariance sets, we'll often use the Lyapunov function itself. D could be all x, for instance, where v of x is less than or equal to some scalar level set. Yeah.
So if we wanted to make the invariance set like the whole space, is that where we need the radially unbounded
Yes,
condition as well?
exactly right. Yeah.
Why does not having that mess things up?
So the question is, why do you need the radially unbounded condition? There's a simple example, which I have in the notes actually, because you need at least one example, but then you believe it's possible. But basically, you can be going downhill, but still, you can go downhill at a place where your dynamics are still taking you away from the origin faster than you're going downhill. You can construct functions that are not radially unbounded, okay, where you basically can never, you can always go downhill, but you're walking away from the origin. And there's a simple example that you'll see in the notes.
So will we need that for any unbounded invariance set?
Yes. Yeah. I mean, for a Lyapunov argument on an unbounded invariance set.
Like if I wanted to show like for any positive value that converges to 0, but I didn't care about anything less than 0, would you just need radially unbounded in sort of the directions you care about?
You can certainly make more tighter cuts. Yeah, I think radially unbounded is a relatively simple condition that captures it, but I'm sure there's tighter conditions that could achieve the same. Yeah. Okay. Does the mechanics of that make sense? So this worked here. This was sufficient to prove the region of attraction because x between -1 and 1, okay, was a sublevel set of V. Right? That V less than 1, strictly less than 1 here, was caused an invariant set. I knew that once I was inside -1 and 1, I won't leave, and I know that V dot is less than 0. Together, those give me the condition that certifies that this region is inside the region of attraction. I use the word is inside the region of attraction, okay? Because having a Lyapunov function only says that, it doesn't say you found the biggest invariant set. It could be the region of attraction is even bigger, yeah.
Could you clarify again what's level set and what's an invariant set?
So an invariant set, the definition of an invariant set, it says if my system starts in this region, it will not leave this region. As the dynamics evolve, you'll stay inside the region. One way to get an invariant set is to have a Lyapunov function where you know that V is going downhill over some region. That means a sub-level set, just like the energy of the pendulum. That's maybe the best way to say it. So what's an invariant set for the pendulum? Any set where the energy is less than or equal to some number, right? Because I know I'll never go outside by gaining more energy. Having the derivative condition match makes the sub-level sets of V invariant sets. Once you're in the land of Lyapunov, that's the natural specification of an invariant set. Sure. Okay. Yeah.
Are there any subtleties if the sub-level set is not convex? Like if you have holes in this?
Ah, see, that's exactly what I wanted you to be thinking of, right? So good. That's the counterexample that I want you to think. But it can't happen. Okay. So the theorems are strong enough to protect you from that. So let's just say, I mean, what if I had a V like this, right? Let's say V of x, x. And I said that V of x is greater than 0. Okay. And I said V dot of x is strictly less than 0. But it can't be strictly less than 0 away from the origin at those. If you have local minima, then you can't satisfy the Lyapunov conditions over these areas.
That is V dot or V?
This is V.
Right. But like, even if V goes up, as long as your V dot doesn't go up, it's fine, right?
So in the statement of the region of attraction, I try to use asymptotic stability, where you're strictly going down. So certainly you can't be V dot less than or equal to 0 here, right? Because partial V partial X is 0, which means V dot is 0, right? So you can't have a asymptotic stability region of attraction that goes to the origin. Yes? In the case where you're talking about less than or equal to 0, you can satisfy that here, but that's okay. That's why the stability in the sense of Lyapunov is different. It doesn't say you get to the origin. It just says you don't leave too far. So the conditions are sufficient. Even if those exist, but you satisfy all the conditions, that certifies only that you will not go too far from the origin, not that you will get to the origin. You need strict decreasing to get to the origin. And that rules out non-convex Lyapunov functions like this. Those are exactly the right questions. Yeah? Okay, so that's why I mean it's actually subtle. Like they look like simple equations, but they imply something fairly sophisticated about the functions that you can find that satisfy them. Do people get that? Okay. All right, here's a, someone told me the other day that I sometimes say there's like an aha moment, and nobody says aha. Like the people are like, not really. This one's going to be an aha moment, okay? So get ready. Okay, get ready. I want to say, what's the relationship to dp, right? I said it at the beginning, but I want you to now appreciate it. Now that we understand the basic mechanics. To dynamic programming. Remember, dynamic programming, we had, for instance, this Bellman equation, min over u, L of xu, plus partial j, partial x, f of xu, right? These are the conditions of optimality. This thing, you know, today I've just been writing that as dj dt, that's the sort of, or j dot, that's the analogy, right? And we said for the minimizing u, you know, for the optimal policy, if I were to insert that back in, what this means is that for the optimal u, I have to obtain 0, right? So that means that dj dt, j star, these are stars, has to equal negative L of xu star. Those are the conditions. We wrote that before when we were talking about dp. And that's hard to find a j. This is a partial differential equation. It's hard to find a j that satisfies that everywhere, that's going downhill exactly the rate, okay? What are we doing with Lyapunov? We're doing almost the same thing. We're saying dv dt, but we're doing a much easier version. Rather than saying it's going down at exactly some rate, I'm saying just tell me it's going down at all, right? Think of it as a relaxation of this hard equation into a soft inequality constraint. And if you have this satisfied, that's enough to say that you're going to get to the origin eventually, but it gives up on optimality. Okay? Aha? Yeah? Kind of? Thank you for whoever did that. Yeah. Okay. So there's exactly one j that satisfies these equations, but there are many v's that satisfy this equation. And in fact, you can satisfy, you know, when we'll get later to seeing how Lyapunov functions can be used for different tasks, you could even satisfy multiple tasks at the same time by having, having this condition satisfied for multiple tasks. But that doesn't really make sense in this case. This is a softer condition, and it makes the search for these things easier. Okay. Now there's more connections. So if you choose a cost that's only positive, then of course the optimal cost to go is also a Lyapunov function. Right? So in all of our candidates we said, the cost is x transpose qx plus u transpose ru, for instance. It was always positive. I guess I only give cost, never reward. Sorry. Okay, but in that condition, the cost to go, if you can find it, is a Lyapunov function. And what's interesting, even if you find an approximate cost to go, if you only satisfy this like in a neural network least squares sense, you could still find out that it might not be perfectly optimal, but it could be good enough to guarantee you'll get to the goal. Or not run into a pedestrian or other things as we generalize it. Okay, that's the aha moment, right? So hopefully that works. And it's gonna change the landscape of tools we can use to search for this. We're gonna use convex optimization even for nonlinear systems often to find certificates, where we've been unable to do that except in very specific cases for the optimal cost to go. Yeah.
Does this let us say anything about how robust this suboptimal solution is to disturbances?
It's a great question. So it is exactly the tools that we need to talk about robustness to disturbances, but we haven't done that yet. So what you'd like to say, for instance, one spelling of that would be to say, no matter what disturbance could be happening inside some set, I'm always have at least that v dot is less than or equal to 0. Right? So if I had, for instance, f of x plus some disturbance w, and I said, but w is inside some set, and no matter what w is, I'm always going downhill, then you can say you're robust to disturbances. And we'll do that carefully in higher dimensional systems and everything too. Okay, so there's one detail that I want to just at least mention, which is that remember how there was a subtlety even in the pendulum argument that v dot was, so I tried to say that I know that the pendulum is asymptotically stable, but the energy is only negative semi-definite. Energy dot was less than or equal to 0, but sometimes it was 0. So there's one extra tool called Lassalle's Invariance theorem that helps you bridge that gap. So let me just say that here. So if I have that v of x greater than 0, v dot of x less than or equal to 0, which would normally only be good enough to prove stability in the sense of Lyapunov, I want to still be able to say that it's asymptotically stable. Okay? It turns out that the statement you can make is that having these conditions is enough that says that v dot will go to 0 as t goes to 0, as t goes to infinity. And that implies that x goes to the largest invariance set. With v dot equal to 0. Okay, so the conditions that we used for stability in the sense of Lyapunov imply something a little bit stronger, which says that actually v dot's going to get to 0, and that x must be in the largest invariance set. The proof of it is a little delicate, but the intuition is exactly what we needed for the pendulum. Remember what I said was the damped pendulum, so the energy is almost always going downhill, but every once in a while, every time it changes direction, theta dot is equal to 0. So instantaneously, energy dot is equal to 0. But that state is not an invariant set. So it turns out that these conditions say that I will eventually get to the largest invariant set where E dot is equal to 0, and that's the bottom. Okay, it just basically, it evokes that same idea that if you're not staying in the state, then you won't get stuck. You'll always end up in the place where it's an invariant set. Okay. That's really just a subtlety. That says, if you can only find a v dot that's less than or equal to, you might still be able to say asymptotic stability. Okay, so let me, oh yeah, please go ahead.
So then to be very precise with the case of the pendulum, it's not, because that invariant set is really small, it's a point, but it's the only one. So that's...
If you want to be really precise, it's actually, this one is an invariant set, or this is an invariant set, okay? And this one's an invariant set, and this one's an invariant set. So actually the largest invariant set is the union of all the other invariant sets, depending if you call those the same or not, okay? And so that the theorem actually just says that I will get eventually to the one of the fixed points. All right, so I want to end by showing you an example of how Lyapunov function can be useful for control, okay? And we're going to do much more than this, but just a teaser, okay? So I will leave my aha. Don't want to erase that. Oh, I should say there's a talk right after this, so I normally stick around and answer questions, but I'm going to run today. So ask questions if you have them now. But yeah, today I have to run at 4. Okay, here's an idea for control of swinging up the pendulum that is motivated and actually certified by a Lyapunov argument. Okay? So recall the homoclinic orbit. I only called it that quickly, homoclinic orbit, but you know it well. It's the eyeball itself. This is the E equals mgl orbit. It's called the homoclinic orbit because it visits the fixed point. Okay. Some people would call it a heteroclinic, depending on if you call it the same fixed point or different. Okay. Homoclinic orbit, which is E equals mgl. Okay, so here's my idea for swinging up the pendulum. I'd like to make a Lyapunov function that's 0 is obtained on that orbit. And I want to kind of have a quadratic form. I can't draw it very well here on the board here, but I want to have a quadratic bowl that kind of goes away from the eye, right? So it'll be higher here, and 0 there. And if I can have a Lyapunov argument that drives me towards that eyeball, then I know actually the trajectory will eventually drive me over to here. I'll just ride the wave. Okay, so how would I make an energy, a Lyapunov function, and therefore a controller that would kind of get me to go in that direction? So if I just write the same thing I wrote before, but I'll write it in a slightly different form here. So let me just do the undamped case. It's easy to put the damping back in. That's not a thing. But let me just write it with a U for the shoulder, or for the torque at the base, because I need to have a controller to put it in. Then if I do dE dt with this, remember I got negative b theta dot squared, but the generalization of that is just that it's u theta dot. What we saw before was when u equals negative b theta, then I got negative b theta dot squared. Okay, but generally it's just And this is, mechanical engineers know this, this is torque times velocity. That's the rate of change of energy. Okay, here's my Lyapunov candidate. Let me choose, I'll put a half in there just to make the math clean. I'll choose that the energy at some state minus the desired energy squared. I'd like to find a controller that goes downhill so that the energy goes towards the desired energy, right? And this is going to just be MGL for me. Let me call E tilde is the energy minus the energy desired, just the error energy, if you will. Then dV dt is going to look like, if I 2 times E tilde, it's going to look like E dot of x times E tilde. And E dot of x is just U theta dot E tilde. That's just taking the gradient of this, multiplying it by my, adding in my E dot, which I learned about, and I just get the form here is simple. So sometimes the Lyapunov function just almost tells you the control. So I can choose a control that makes that a valid Lyapunov function over some domain. So why don't we choose U equals negative K theta dot E tilde, where this is just some control gain. Just a control gain, control parameter. If I choose that control, then as long as theta dot's not 0, I can get the dV dt equals negative K theta dot squared E tilde squared, which is less than or equal to 0. Okay, and it obtains, this controller, of course, obtains its minimum at the homoclinic orbit. And it turns out that's a beautiful controller for swinging up a pendulum. Okay, so actually first I hope you'll play with this later too, but this is just the eyeball, and I plotted a bunch of different colored trajectories here, starting from lots of different initial conditions, okay? And what do? They do this beautiful swing up, converge to the eyeball, right? That argument says that E will go to the E desired. But if you look carefully, there's one thing it doesn't do. It doesn't actually stop when it gets to the top, okay? It just says I'm going to be on the manifold. If I'm even arbitrarily off the manifold, I'll just go around and do it again, okay? So actually, this isn't a complete controller. What we're going to do is we're going to take that controller, and then when we get close to the origin, we'll switch to an LQR controller, okay? And how close you are to the origin turns out to be something we can compute the region of attraction, and we'll be able to do that perfectly. But you add them together, and you get beautiful energy pumping control of the pendulum. Okay, I'm randomly restarting it at initial conditions. It's pumping up energy. If you ask, is it robust? This is like ridiculously robust. What parameters did I have to know? I needed to approximately understand the energy and measure the velocity. But if I even get the sign close to right, it's so robust. You could say the mass was 10 times different than it actually is, and it's going to work. What if you have torque limits? No big deal. It's just going to put a little less energy each time, right? It's just exactly, it's like what all control should be like, right? It's a simple controller, that's like the simplest controller. It does exactly the right thing, and it's super robust. I long to get that out of all my other optimizations, okay? And it comes right out of the Lyapunov argument. Good, so that's, welcome to Lyapunov, and we'll do a couple more, we'll build more computational tools next time.